Welcome back. Today we're going to take a look at the different parts of an atom. We've looked at Crookes and JJ and Rutherford and what they contributed to the atomic model and the atomic theory. Now we're going to go ahead and take a look at what the parts of an atom actually are. So let's try and get this thing going. First one, the protons. The protons are larger particles and they're in the nucleus of an atom and they are positively charged. They're fairly heavy and they are positively charged is the main thing that you have to remember about those. Now, how do you figure out how many protons you have? It's always the same as the atomic number. Now you can look at the periodic tables I have hanging in my classroom. They're in the back of the book. They're posted to the ceiling, and I gave you your own individual periodic table. But on there, on each box, in each element, you can see there's two numbers. One happens to be larger, and I'm talking larger in quantity, not larger in size. Take a look at beryllium. Beryllium, in that box, you can see a 4 and a 9.0112. Well, what one is the atomic number? The atomic number is the 4. Okay, so we can figure out there's 4 protons in beryllium itself. What is the 9.0122? Well, that's the atomic mass, and we're going to need that for the next guy. So we have protons taken care of, large particles, center of an atom. Next thing we have is neutrons. Neutrons are also in the middle of the atom, and they're also fairly large particles that are in the middle of an atom. Now, they are neutrally charged, thus the name neutron. Okay, so how do we figure out how many neutrons we have in an atom such as beryllium? We'll use the same one. It's the atomic mass subtract the atomic number. Each of these protons here weigh 1 atomic mass unit, and each of these neutrons essentially weighs 1 atomic mass unit. So something like beryllium, it has an atomic mass of 9.0122. Well, we would have to actually round that one out. We would take 9.0122 and round it to 9. That's the closer number. We would take 9 minus the atomic number of 4 to get 5. So we could see then that beryllium has 5 neutrons inside of it. Now I do want to touch on, why is beryllium, why isn't the atomic mass just 9? Why is it 9.0122? Well, the reason is isotopes. In a normal sample of beryllium, most of the beryllium will just have an atomic mass of 9. But some of the beryllium will be an isotope. It will be an atom that has extra neutrons. And those extra neutrons are what's going to throw off the atomic mass, and that is what's going to give us an atomic mass of 9.0122. It's going to throw it off just a little bit. But for our purposes, we're taking a look at normal beryllium, not an isotope of beryllium. For our purposes, we can just round out that atomic mass. Now the last one is electrons. That's the last particle that we see in an atom. Now how do you figure out how many electrons there are? Once again, it's the same as the atomic number. Electrons are generally further on the outside of the atom. They're zipping around out there, and we're going to talk about more models later on. Electrons weigh very, very little. Electrons weigh almost nothing. I don't know the numbers exactly, but electron is something like 1/2700th of a proton. So protons are heavy inside of an atom relative to the atom. Electrons are very, very light. Essentially, they don't weigh anything, but they do have a charge, and their charge is actually equivalent in strength to the charge of a proton. So, and once again, that's why there's the same number of protons and electrons in a neutral atom. If they had more electrons, it would be negatively charged. If there were less electrons or more protons than electrons, you would have a positively charged atom. So just in review real quick, we got protons in the middle, neutrons on the middle, electrons zipping around on the outside. On the next video, we're going to go ahead, we're going to take a look at the electron cloud model, one of the biggest, one of the best models of atoms that we have today. And it's amazing to see God's power in the makeup of those atoms right there.